So today what we're going to look at is how the derivative and the second derivative affect our functions, and how we can really get a clear picture of what a function looks like based on its derivative and second derivative. So one thing that we talked about last time and the time before is that whenever our derivative was positive, our function was increasing, and then whenever our derivative was negative, our function was decreasing. And hopefully you all remember that from when we were practicing graphing the derivatives from the graph of a function that we were given. That, right, with the derivative is positive, it increases, and when the derivative is negative, the function decreases. So this is an important point that you need to know. I'm going to make one extra point about this is note that these are on closed intervals. Now, I have a little bit of a problem with these being closed intervals all the time, but the College Board wants you to indicate that they're on closed intervals when you talk about increasing and decreasing. So you'll have to use closed intervals. I'll explain in a second why I disagree with that, but we're going to use the closed intervals just because I need you to get used to it for the AP test. So let's see if we can do this first problem here. So we want to figure out where the function f of x equals x squared rises and falls. So where is f of x increasing and where is f of x decreasing? So we're just going to use the derivative to do this, even though we already know the answer, right? We know when x squared is increasing and we know when x squared is decreasing, but we're going to use the derivative to do it. So we're going to find f prime of x. What's f prime of x? If f of x is x squared, should be
2x.
2x, right? All right, so now what we're going to do is we're going to figure out all of the places where this could potentially change signs. So one place where a function, 2x, could change signs is when it's equal to 0, right? It could change signs at a critical value. So that would be at x equals 0. And also it could change signs if that derivative is undefined. And so 2x is never undefined. So the only value at which 2x could change signs is at x equals 0. And so the only place where our function x squared could potentially change from increasing to decreasing is at x equals 0. And so then all we're going to do is we're going to make what's called a sign chart for the derivative. So we're going to take a horizontal number line and put our value of 0 that we found on it. And we're going to plug in a value that is greater than 0 into our derivative and a value that is less than 0 into our derivative and see what we get. So if you plug in a positive number like 1 or 2 or 1,000 into our derivative, right? Our derivative was 2x. You get another positive number. You guys agree with that?
Yep. Yeah.
Right. So anything that I plug in greater than 0 should make my derivative positive. I know that there's nowhere beyond 0 that's going to change again, because the only place where my derivative could change signs was at 0. So I know that it's always positive over here. And if the derivative is positive, then that tells us that f is increasing on that interval. Good so far?
Yeah.
All right. And if we plug in something less than 0, like -1 or -2 or negative 10,000, we end up with a negative number over here. We plug it into our derivative, and that tells us that on this entire interval, our function is decreasing, because our derivative is negative. So that tells us that our function is increasing from 0 in a bracket closed interval to infinity. And infinities are never done with brackets no matter what, even on increasing and decreasing intervals. And our function is decreasing from -infinity to 0 with a bracket. And so that's the problem I have with it, is what we're saying here is that our function is both increasing and decreasing at 0. Whereas really, I mean, we know what f of x equals x squared looks like, right? It's just a parabola. It's doing neither at x equals 0. That's the point where it's not increasing or decreasing, where it's completely flat. But the College Board wants you to indicate it with brackets. So this would be our answer to this question, that this function increases from 0 to infinity and decreases from -infinity to 0. Here's our proof. our sign chart is our proof and our derivative is our proof. Obviously, we already knew that was true because that's a really simple function, but most of the functions we'll deal with, we won't just know right off the bat. Any questions on that? Everybody good with that?
Yeah.
Yep.
All right, perfect. So let's look at x cubed minus 4x. So that one we probably don't know right off the bat exactly where it's increasing and decreasing, but we should be able to use our derivative to figure that out. So what's the derivative of x cubed minus 4x?
3x minus 4.
3x
Oh, sorry,
squared.
3x squared. Yeah.
3x squared minus 4. And so we need to do two things with this. First, we need to figure out when is it equal to 0 and when is it undefined. Well, it's never undefined, right? So we can ignore that for now. And if we got polynomials, we know that they're never going to be undefined. So that's pretty easy, but not everything we'll have is a polynomial. And so now we'll set this equal to 0 and solve, right? So if we solve this, we end up with x squared equals 4/3 or x equals positive or negative 2 over root 3. Everybody agree with that?
Yep.
Do we need to rationalize that and make it 2 root 3 over 3?
We
No.
have to.
No, we don't have to. I don't care about that. Every other math teacher probably told you, yeah, you got to rationalize that, but I don't care. And the College Board doesn't care. And no sane person cares. All right. So what about our sign chart here? We're going to put on a negative 2 over root 3, and we're going to put in a positive 2 over root 3. And now we just need to plug in some values into our derivative. To our derivative of 3x squared minus 4 that are on each of these different intervals. So let's figure out what is f prime of 0. F prime of 0 is positive or negative?
Negative.
Negative, right? It's less than 0. It's negative 4. So in the middle here, we have negative, and we should be decreasing. What if we plug in something that is more than 2 over root 3? What's something more than 2 over root 3?
2.
Okay, 2 is, yeah, okay, that works. I was going to say like 10,000, but 2 works. Plug in 2, you get a positive or a negative number?
Positive.
Positive if you plug it into your derivative, right? So now we're increasing. And something less than negative 2 root 3, we could use negative 2, or we could use negative 10,000. When we square that, it becomes positive, right? A positive 4 times the 3 is 12, minus the 4 is positive again. So on that entire interval, our function is increasing because its derivative is positive. Good.
If we're working out this problem, do we need to plug in, like, do we need to show the is less than 0 is greater than 0? Like, do we need to show that, or can we just put the sign chart?
No, just the sign chart is fine.
Okay.
Yeah, I'm writing it out for now just because it's the second one we're doing. But
Do you also want us to put the arrows for increasing or decreasing, or just positive and negative?
either way is fine. Doesn't really matter.
Okay.
Yeah. All right. So we would then state that this is increasing on the interval negative infinity to negative 2 over root 3 bracket union 2 over root 3 to infinity. And it's decreasing on the interval between. Any questions on that?
Nope.
No.
All right, cool. So there's a lot of information here. So if we have a critical value and our derivative goes from positive to negative, then we must have a local max. That's the first thing. So if we go back and look over here, our derivative went from positive to negative, which meant our function went from increasing to decreasing. We got to have a local maximum there. And same here, if the derivative changes signs from negative to positive at that value, then we have a local minimum there. So from negative to positive, the function goes from decreasing to increasing. We must have a local minimum. And if there is no sign change, then there's no local extrema there. So this is how we're going to be able to determine locations of local maxima and minima. Okay, and then we can do the same thing with the endpoints. If at an endpoint the derivative is positive to the right of it, then we have a local min, and vice versa. That makes sense?
Yeah.
Okay. So what we're going to try to do then is use the derivative test to find any local extreme values. We're also going to figure out if any of them are absolute extrema. And we'll also determine when the function is increasing and decreasing, because why not? So we'll do that for this function, x cubed minus 12x minus 5. So what's the first step going to be?
Find the derivative.
Find the derivative, f prime. What's f prime? The
3x squared minus 12.
Exactly. Is that ever undefined?
No.
Never undefined, but it does equal 0, right? When x is
2, -2.
positive or -2. We could write this out as 3 times x plus 2x minus 2. And it's often helpful to have the nice factored form because it makes the sign chart a little bit easier, especially when your derivative is not such a simple one like this one is. So we'll make our sign chart. We'll put on -2. We'll put on 2. What's something between -2 and 2? It's really easy to evaluate.
0.
0, right? So if we plug in 0 to our derivative, we get a negative. We can also see that here. If I plug in 0, it's a positive times a negative, right? So decreasing. Plug in something more than 2, like 1,000, then we're going to end up with a positive times a positive times a positive. And if I plug in something less than -2, like -1,000, this is a positive times a negative, which gives you a positive. So do we have any local maxima?
Yes.
All right. We have a local maximum at what value? X equals -2. So we're going to need to figure out, this is our derivative. So we're going to figure out f of -2. What's f of -2?
11.
Looks like it's 11. And what's f of 2? Where we might have a local minimum, or where we do have a local minimum.
-21.
-21, yep. So we have a local max of 11 at x equals -2, and we have a local min of -21 at x equals +2. And we could also say that our function is increasing, -infinity to -2, 2 to infinity, and decreasing -2 to 2. Good with that?
Yeah.
All right, now, the last thing it asked us was identify if any of those are absolute extrema. So is that local max an absolute max of this function?
Nope.
And how do you
No.
know that? Why do you know that it's not?
If you plug in like 1,000 or something, you're going to get a number a lot higher than 11 or a lot lower.
Right.
On the negative end.
As x goes towards infinity, what's the limit as x approaches, what's the limit as x approaches infinity of f of x? It should just be
Infinity.
infinity, right? And, you know, basically the same idea. What's the limit as x approaches negative infinity of f of x? It's negative infinity, right?
Infinity.
And so we know that our function gets larger forever as we go toward the right, and it gets smaller forever, you know, and decreases, we say decreases without bound or increases without bound as it goes to the left and to the right. And therefore it's definitely not going to have any absolute extrema because it's always increasing higher. Now, we could have a function that's always increasing here, but it might be increasing towards an asymptote. So we want to check and see if it's going towards infinity or negative infinity to make sure about the absolute extrema. Does that make sense?
Yep.
Yeah.
Yeah, and we'll see some examples of that. today or tomorrow. So, let's take a look at this one. X squared minus 3 times e to the x. So now, the last couple, right? I mean, cubic function, parabola, another cubic function. You probably already had a pretty decent idea of what those looked like, but function x squared minus 3 times e to the x, you may not be anywhere near as clear what that one may look like, right? So what are we going to need to do? We're going to need to take
Take the derivative.
Right, and so since this is x squared minus 3 times e to the x, it's a product of two different functions. We'll take the derivative using the product rule. So x squared minus 3 times the derivative of e to the x, which is what?
E to the x.
E to the x, and then plus e to the x times the derivative of x squared minus 3, which is 2x. We end up with that. And how can we simplify that down to see when it's equal to 0 and when it's undefined?
You factor out e to the x.
Yep, factor out e to the x. We have e to the x times x squared plus 2x minus 3, or e to the x times what? We can factor that hopefully, x plus 3 and x minus 1. Yeah?
Yeah.
Yeah.
So is this ever undefined? Are there any x values I cannot have as a power e to that power? Are there any real numbers e to the?
No.
Nah, that's always defined, and I can always add 3 to any number, and I can always subtract 1 from any number. So it's never undefined. Make sure you note that. Okay. And then when does it equal 0? Well, when any piece of it equals 0, right? It's 3 different pieces of it. So if this one was 0, it'd be 0 times some stuff, which would be 0. Or if this one was 0, it'd be 0 times some other stuff, which would be 0. And same with the last one. So when does e to the x equal 0?
Never.
Never. Right? Yeah, never. Okay, what about x plus 3? That gives us -3. And x minus 1 gives us 1. Everybody good with that?
Yep.
Yeah.
All right, so we've got our two critical values, 1 and -3. We know those are the only places where we might have local maxima or minima. And so we're going to make a sign chart with -3 and with 1 for our first derivative. And we'll plug in values. What's something that's more than -3 but less than 1?
0.
0.
0. 0 is often a nice, easy one to check, right? Plug in 0 to usually your most factored version here, just to make it easier. E to the 0 is positive. 0 plus 3 is positive. 0 minus 1 is negative. 2 positives times a negative makes a negative. Good?
Yep.
Yep.
Okay. Something greater than 1, like 1,000. Positive times a positive times a positive, right? So positive. And something less than -3, like -1,000, is going to be a positive. E to the -1,000 is just a tiny little fraction, but it's still a positive number. And then a negative and a negative makes a positive. Everybody good with that also?
Yep.
Yep.
Good. All right. So all we need to do then is figure out the value of the function at -3 and the value of the function at 1. I give us another page for this. So what's f of -3 and what's f of 1? What was our original function? X squared minus 3 times e to the x, right? So that'd be 9 minus 3 is 6 times e to the -3, or 6 over e cubed. And then this one would be x squared, 1 minus 3 is -2 times e to the first, so -2e. Everybody good with the evaluations there?
Yep.
Okay. So then, -3 was our max and 1 was our min. So we'll say we have a local max of 6 over e cubed at x equals -3. And we have a local min of -2e at x equals 1. Good or no? Okay, so then the question is, are either of those an absolute max or an absolute min? And so we know that our function should be decreasing as we go to negative infinity and increasing as we go to infinity, but we need to check the asymptotes and see if there's any asymptotes. So we'll do the limit as x approaches infinity of f of x. And as x goes towards infinity, what does x squared minus 3 become? Becomes very large, right? And
Yeah.
e to the infinity is also very large. So we end up with a very large number times a very large number. So as our x values get very large, our function's values also get very large. So our local max is probably not going to be an absolute max, right? Because, I mean, it's definitely not going to be, because this is going to infinity. We're going to get much larger than 6 over e cubed. What about the limit as x approaches negative infinity of f of x? Well, that becomes e to the negative infinity over negative infinity squared minus 3. And e to the negative infinity becomes negative infinity squared minus 3 over e to the positive infinity, right? And which one of those is increasing more rapidly?
E to the infinity.
E to the infinity is, which tells us that this limit is what?
0.
0. And so that means that to the left, we have a horizontal asymptote of y equals 0, which means that even though our function is decreasing forever, it's decreasing and approaching 0. So we could draw a real basic sketch of this graph. It's going to look something like, approaching 0 here, having some max up here at -3, then dropping down, having some min, and then it's going to come back up and increase forever. Right, so we're increasing from negative infinity to -3, decreasing from -3 to +1, and then increasing again from 1 to infinity based on our chart. Does that make sense to everybody?
Yeah.
All right, and we would then say that our local min is also an absolute minimum. But our local max is just that, it's just a local max. And let's, just for fun, let's take a look at the graph of this on Desmos. We had e to the x times x squared minus 3. And that's basically what we had, right? We had this function that as we approached negative infinity was approaching a horizontal asymptote. It had this little bump up here that made it a local max, it dropped down to a local and an absolute min, and then it increased afterwards. Right? Good or no?
Good.
All right. Cool. So in order to get an even better idea, because if you look here, my graph doesn't look super great, right? I mean, it showed the basic trajectory of that curve, but I didn't do a great job with it. We can get a much better idea of what a function looks like if we know also about its concavity. And so we've talked a little bit about concavity before, but a function will be concave up on an interval if its derivative is increasing. And if the derivative is increasing, that means that the derivative of that must be positive. So if y prime is increasing, or if y double prime is positive, then our function should be concave up and look like this, or generally in that shape. And if our function has its derivative decreasing, or the second derivative is negative, it should be concave down and look something like this. And so we'll do a similar process using second derivatives as we did with the first derivatives. We did the first derivatives to see if it's increasing or decreasing. Well, we'll use the second derivatives to see when it's concave up and when it's concave down. Does that make sense to everybody?
Yeah.
All right. So we should already know what the concavity of y equals x squared is. What's the concavity of y equals x squared?
Concave up.
And it's always concave up, right? It's always concave up from negative infinity to infinity. And so we're going to show that that's true right now, because what's the derivative? Our derivative is
2x.
2x, and our second derivative, which tells us the concavity, is
2.
2. When is 2 positive? Always, right? This is greater than 0 for all real values of x, right? 2 is always positive. Therefore, this function must always be concave up. Good or no?
So when its second derivative is positive, it's concave up, and when the second derivative is negative, it's concave down. Is that
Right.
right?
So yeah, so the derivative increases if the second derivative is positive, and if the derivative is increasing, that's when we're concave up. And the same thing here. The derivative is, if the derivative decreases, if the second derivative is negative, and therefore it'd be concave down. And if we think about it, if we have a function, right, and this function's concave up, right? Well, what's happening to these slopes of the tangent lines? They are getting larger, right? I started with a very large negative, then a less large negative, right? And then a negative, started maybe -4, then -2, then -1, then 0, 1, 2, 4, right? The slopes of the tangent lines, the derivatives are increasing, gives me a concave up function. The slopes of the derivative are decreasing, like from 4 to 2 to 1 to 0 to negatives, then I'm concave down. Does that make sense? Does that help?
Yeah.
Okay. Cool. All right, so let's see if we can determine the concavity and any changes that we might have in concavity of the function 2 plus sine x, just on the interval from 0 to 2 pi. So what's the first thing we need to do?
Take the derivative.
Take the derivative, right? Y prime is what?
Cosine x.
Cosine x. And then we'll need a second derivative. So what's y double prime?
Negative sine x.
Negative sine x.
Negative sine x. Is that ever undefined?
No.
Right, never undefined. So when does it equal 0? On the open interval from 0 to 2 pi, it equals 0 when x is what?
0 and pi.
Right, well, I got an open interval on both sides there. So really just,
Oh, that's right.
Right.
Just pi.
but yeah, I mean, if that was closed, yeah, you'd be right. So now what we'll do is we'll just make a sign chart with our second derivative. We'll put pi in the middle. And since we're only talking about the interval from 0 to 2 pi, we're still going to put those endpoints and just make sure that any values that we plug in are between 0 and pi and between pi and 2 pi. Does that make sense?
Yep.
Yeah.
All right, so what's something between 0 and pi? Pi over 2? Yeah?
Yeah.
And what is the sign of pi over 2? Or the negative, we'll say the negative sign of pi over 2 is what?
-1.
-1, which means that it's negative everywhere between 0 and pi, which means that the function is concave down. And then if I plug in something between pi and 2 pi, like 3 pi over 2, we should end up with a positive 1, which will tell us that on that interval, our function is concave up. And just because they feel the need to contradict themselves, the College Board will allow you to put these ones in open intervals. So this is concave down from 0 to pi, and it's concave up from pi to 2 pi. Good or no?
Yeah.
And if we were to look at our function, 2 2 plus sine x. And if we look from 0 to pi, which is right around here, right? Our function is concave down. And then it switches at pi to become concave up until we get to about 2 pi, somewhere over here. Everybody see that?
Yeah.
All right. Cool. So we've also already talked briefly about points of inflection. So remember that points of inflections are just places where the function changes its concavity. So back here on this last one on page 9 here, we should have had a point of inflection at x equals pi. We weren't asked about it, but we have one. So anytime the function changes concavity, we have a point of inflection, just so long as our function exists there, right? And has to have a tangent line there. It has to exist. So let's see if we can find all the points of inflection for y equals e to the negative x squared. Let's see if there are any. And if there are, what they are. So how are we going to do that? First off, what do we need to take? A first derivative?
Yeah.
All right, so what's our first derivative of e to the negative x squared?
That'd be 1 over, well, yeah, we'll just do 1 over e to the x squared. Or, actually, I'm a bit complicated about
Let's
that.
just do this. This is just y
Yeah.
equals e
Yeah.
to the u, right?
Yeah.
So e to the
So
negative
e
x
to the
squared.
negative x squared times negative 2x.
Good. Everybody good with that?
Yeah.
That's just our
Yep.
rule for exponential functions. E to the u is e to the u du. So e to the negative x squared times negative 2x. And then the second derivative will become a little bit more complicated. Y double prime is what? We'll need to use the product rule for that.
Yep.
Yeah.
So negative 2x times the derivative of e to the negative x squared, which we just found to be negative 2x times e to the negative x squared, and then plus the derivative of negative 2x, which is negative 2, times e to the negative x squared. Good or no?
Yep.
All right, and what can we factor out of both of those?
E to the negative x squared.
E to the negative x squared. And what's left here? 4x squared and a minus 2. Everybody good with that?
Yep.
All right, 1 second. All right, sorry. So when is this undefined?
Never.
Never.
Yeah, never undefined, right?
Never.
I can take any number and square it and make it negative and raise it as a power of e, and I can take any number and square it, multiply by 4 and subtract 2, right? Never undefined. Don't worry, eventually we'll get some where they are undefined. But never undefined. And when does it equal 0? Well, can e to the negative x squared equal 0?
Nope.
No.
Nope. E to any power or any number that's not 0 to a power will never equal 0, right? So all we have left is 4x squared minus 2 equals 0, which would give us x squared equals what? 2/4 or a half, or x equals 1 over positive or negative 1 over root 2. Good or no?
Yep.
Okay. So then we'll make a sign chart using our second derivative, because we have to make sure that there's actually a sign change. And if there's not a sign change, then there's no point of inflection. So we got to check for the sign change. So something between negative 1 over root 2 and 1 over root 2 should be 0. Plug in 0. And e to any power is always going to be a positive number, right? So this thing here is always positive. And if I plug in the 0 here, I get a negative. And so it's concave down. Plug in something more than 1 over root 2, like 1,000. And what do I end up with? A positive times a positive, so concave up. And something less than this would be negative 1,000, still positive, and still positive. So concave up. So how many points of inflection do we have?
2.
2 points of inflection. One of them occurs at negative 1 over root 2, and the other occurs at 1 over root 2. And so we will figure out what is the value of y at each of those. So we had what, y equals e to the negative x squared, and we want to know what is y of negative 1 over root 2, and what is y of 1 over root 2 to find the actual points. So plug it in. First off, if we square 1 over root, or negative 1 over root 2 and 1 over root 2, we should get the same thing. Should get what, a half for both of those. So both of them just equal e to the negative 1/2, or 1 over e to the 1/2, or 1 over root e. Everybody good there?
Yep.
And our points of inflection then are negative 1 over root 2, comma 1 over root e, and 1 over root 2, comma 1 over root e. And if we want to, we could have listed the intervals on which it was concave up and concave down, but didn't ask us to, so we don't necessarily need to. Any questions on that? All right, so a couple of things that I want you to keep in mind. As you go through and do tons of these problems, you're possibly going to get a little bit lazy and forget to do the sign chart and check. And I want to encourage you that you always need to do the sign chart and check, because sometimes the second derivative might be 0 at a place where there's not an inflection point. Okay? So let's take the case of f of x equals x to the 4th. Our first derivative should be 4x cubed. And our second derivative should be 12x squared, right? When does this equal 0? Should be at x equals 0. Okay. I'll plug in a positive number into your second derivative, and what do you get? You get a
Positive.
and plug in a negative number to your second derivative, and what do you get?
Positive.
Positive, right? And so there's no change in concavity here. It's concave up from negative infinity to 0, and concave up from 0 to infinity. So really it's concave up for the entire domain of this function from negative infinity to infinity. And there is no point of inflection at 0. So just be careful with that. And the other thing is make sure that you check when your second derivative doesn't exist. A lot of people start forgetting about that because it doesn't happen that often. But if you look at something like x to the 1/3, or the cube root of x, right? Well, where f prime is 1/3 x to the negative 2/3, and f double prime is negative 2/9 x to the negative 5/3. Well, this never equals 0, right? If you rewrite it as negative 2 over 9 x to the 5/3, that will never equal 0, but it is undefined at x equals 0. And so you want to make a sign chart with that for your second derivative and show that when you plug in a positive number, if you plug in a positive to this, you get a positive for the fraction with a negative out in front. And when you plug in a negative number, this x to the 5/3, when you take a negative to that, stays negative. So you have a negative of a negative, which gives you a positive, and you have an inflection point, or a point of inflection at x equals 0. Does everybody see that?
Yep.
All right. So just make sure that you're being careful about that. That you don't start skipping steps just because you're lazy or you feel like it. All right. Any other questions on that before we keep moving? All right. So we have this other thing called the second derivative test for extrema. So, you know, we went through and we were doing our local maxes and our local mins back here somewhere, way back here, right? We made the sign chart, right? We made these nice little sign charts every time to show when it was increasing and when it was decreasing, if it was a max or a min. And sometimes making that sign chart will be a little bit of a pain. And if you are of the case where the derivative was 0, you can use what we call the second derivative test. You can determine the concavity of the function at that point, and from there you'll know if it's a maximum or a minimum. But it only works if the first derivative is 0, not if the first derivative is undefined, and you have to be able to have a value that is not 0 for the second derivative. So let's think a little bit about this. Let's go back to one that we've already looked at. Let's go back to the first one we did. Let's go back to this one. So we did x cubed minus 12x minus 5, and we said that the derivative was 0 at -2 and 2, right? Well, we could have also used what we call the second derivative test. And so our first derivative was 3x squared minus 12. What's our second derivative?
6x.
6x. So if we take 6x and evaluate it at x equals -2, and if we take 6x and evaluate it at x equals +2, we should get -12 and +12. And according to our second derivative test that I just said, if the second derivative is negative, then that tells us that this should have been a max at x equals -2. And if the second derivative was positive, then it should be a min at that value. And that's exactly what we got. We got a max at -2 and a min at 2. Well, why does that work? Should make sense, hopefully. If you have a second derivative that's negative, what does it tell you about that function?
It's concave down.
Concave down, right? And if it's concave down at a place where the derivative is 0, that's got to be a max. And if the function's second derivative is positive, it's concave up. And if the first derivative is 0 on an interval where the function is concave up, that's got to be a local min. Does that make sense?
Yeah.
Okay. So we have 2 potential methods for determining if it's a max or a min. One, which will always work, is the sign chart. And 2, the second derivative test, which only works if your critical values were places where x or where your derivative was equal to 0. Okay, so let's go back here to, oh, look at that. That's the one that we just did that one. Should have done that on this page, I guess. Oh, well. But yeah, that's the one we just did, right? X cubed minus 12x minus 5.
Yeah.
Well, probably don't need to do that again. All right, so what we want to try to do now is see if we can put all of this information together, along with some stuff that we should have already known from previous math classes, like x and y intercepts and all that crap, and draw a really nice version of pretty much any function that we know how to differentiate. So we're going to start with a pretty straightforward one, x to the fourth minus 2x cubed. So I want to see if we can graph this without using our calculator at all and get a really nice version of the graph. So first off, how do we find x and y intercepts of this?
Set the other variable equal to 0 and solve for that one.
Right. All right. So we'll set it equal to 0 to start. X to the fourth minus 2x cubed equals 0. Take out the x cubed, and you get x-intercepts of 0 and 2. And I'm gonna go in and just make each of these one. Each 2 boxes 1 unit. Okay. Everybody good with our intercepts there?
Yep.
Do we need to find a y-intercept also by plugging in 0 for x?
Yeah.
I mean, we could,
Well,
but
we
we already
already
found it. We already have it, right? There's not going to be more than one y-intercept. We happen to get the origin as a point on here, so we don't need to find another y-intercept. There won't be one, or else it wouldn't be a function. So our next step then is to figure out when the function increases and decreases and when it has local maxima and minima. So that'll be a derivative test. First derivative, f prime is 4x cubed minus 6x squared. Everybody agree with that?
Yep.
Okay, so we've got 2x squared times 2x minus 3. If we factor that out, we know this is never undefined, right? So we'll say never undefined, but it equals 0, where? When x equals 0 and when x equals 3/2. True?
Yep.
All right, we'll make our sign chart. Sign chart for the derivative. So what's the thing between 0 and 3/2? 1.
Yep.
Plug in 1, we got a positive times a negative, which gives us a negative. It tells us our function decreases. Plug in a negative number. 2x squared is still positive, but a negative times 2 minus 3 is going to be what?
Negative.
Negative still, right? So our function is decreasing to 0 and then still decreasing from 0 to 3/2. All right, so this value where our first derivative was equal to 0 is not a local max or a local min. And if we plug in something more than 3/2, like 1,000, this is positive times a positive. So we do have a local minimum. Good or no?
So that 0 point like failed to be a local max or local min, like even though it was like in our first derivative test, it came up as like x equals 0. When we did the sign chart, it didn't work, and that's why.
Yep, that's exactly right. So that's the deal, is you have to check on the sign chart to show that it is. And just because it's a critical value doesn't mean that it is a max or min.
Cool.
All right, so let's figure out then. Hold on, somebody said something in the chat. So question came up is, how do I know that the derivative is never undefined? Well, because I know, first off, I know that it's a polynomial, so polynomials exist for all real numbers. But you can take any number and square it and then multiply it by 2, and you can take any number, multiply it by 2 and subtract 3. So as long as there are no x values that make it undefined, as long as there's no x values that, inside of a square root or like a denominator that would make it 0, then it's never going to be undefined. So for any polynomial, we can be sure that it's never undefined. All right, so now we need to figure out what is f of 3/2, just so we can plot that point, because we know that's going to be a pretty important point on this graph. A local min is an important point. So what's f of 3/2? Should be 3/2 to the 4th power, which is what, 81 over 16. And then minus 2 times 3/2 cubed. 3/2 cubed is 27/8. And multiply that by 2, that should be 27/4. And let's see, multiply that by 4 over 4 to get a common denominator should be what, 108 there. And that's 27/16. You guys agree with my arithmetic there or no?
Is it not negative? 81
Oh,
minus
sorry, negative. Sorry, negative 27/16. Yeah. So at 3/2 should be negative 27/16, which is going to be somewhere down about there. Good or no? Hopefully that's good. All right, next thing we're going to do is we're going to take a second derivative to find out concavity. So we'll need a new page for that. So our first derivative was 4x cubed minus 6x squared. So our second derivative ought to be 12x squared minus 12x. Just using the power rule there, 12x squared minus 12x. And I can say, again, since this is a polynomial, it's never going to be undefined. So we'll state that, never undefined, and equals 0. Take out the 12x. It's undefined when x equals 0 and when x equals 1. And so we'll make our sign chart. And if we plug in something between 0 and 1, like a half, we've got a positive times a negative. So negative, concave down. Plug in something more than 1, like 1,000, we have a positive times a positive, so that's concave up. And plug in something that's negative, like negative 1,000, that's a negative times a negative, which is positive. So again, concave up. All right, so we'll see, I know we had the question before about at x equals 0, we thought that maybe it was supposed to be a local min or a max, but our sign chart showed that it wasn't. Well, generally when that happens, generally, not always, but generally when that happens, it's going to end up being a point of inflection. And we'll see that we do. We have a point of inflection at 0, and we know it's 0, 0, right? Because we already found that point. And we have another one at 1, comma something. And so if we plug in 1 to our original function, what was f of 1? F of 1 should be 1 minus 2, or negative 1. So we have a point of inflection at 1, negative 1 as well. Good or no?
What does that mean for a graph, though? Because how do you graph points of inflection? Just because they're...
All right, check this out. It's pretty impressive. Watch this. I'm going to graph this point of inflection. There it is. I did it. 1, negative 1.
Okay.
No,
And it's, but just like the line just continues right through it, right? It's
Yeah,
just
yeah.
an arbitrary. Okay.
I'll show you in a second. I'm just kind of being a jerk because that's what I would normally do if I was in the classroom. I'm just trying to have some fun here. Yeah, it's a point of inflection. So what we need to do is when we draw the actual curve, we need to show that to the left of 1, it was concave down. So it was looking like this. But then at 1, negative 1, it turns into concave up. That's all we need to do. Does that make sense?
Yeah.
So that's what we're going to do. So we know that from negative infinity to 3/2, it's decreasing. So it should be decreasing throughout all of this until we get to this local min, and then it should start increasing. So let's start with what's going on after 3/2. After 3/2, it's increasing, and it's also, because right, 3/2 would be like right here, right? It's also concave up. So concave up and increasing looks like that. From 1 to 3/2, it's decreasing, and it's still concave up. Right, from 1 to 3/2, it's still concave up. So we should have this, just this piece of it looks like a parabola sort of. But then it needs to be, even though it's still decreasing here, it needs to, from 0 to 1, be concave down. So that's got to look kind of like this. And then right there again at 0, 0, right at 0, 0, it still is decreasing, but it switches back to being concave up. And so it should look something like that. So we've just got this point of inflection in there at the origin, and then another point of inflection at 1, -1, and then we've got our local min at 3/2, -27/16. And I know this got a little wavy here. That should be just sort of a nice curve, but that's just my inability to draw nicely. Let's see if I can fix that. Nope. Still no. I know. Perfect. Any questions or issues with that?
Nope.
All right. And just for the sake of making sure we didn't screw this up, let's take a look at x to the 4th minus 2x cubed. And that, you know, is pretty darn close to what we drew, right? Concave up, point of inflection, concave down, point of inflection, concave up, no longer decreasing, local minimum, our x-intercept, and still concave up forever. Everybody all right with that?
So we have 2 derivative tests. The first one shows us whether it's increasing or decreasing, and then the second one shows us inflection points. Is that what they both do? Or?
Inflection points, and then or concave up and concave down. Yeah, when it has intervals of concavity. And
Okay, cool.
when it has points of inflection. That is correct. All right, that was a lot, I think. Is that a lot?
Definitely.
Yeah. So what we'll do is I'm gonna not do the next couple. We'll deal with these other ones tomorrow. I'll let you guys go now, so you can sort of process. If you have any questions, you can feel free to hang around. But if you don't, then that's fine. I will post up an assignment about this, but we're gonna do more with this tomorrow, just more practice with it. So I'm not gonna have it due today. It'll probably be due tomorrow, or it might not even be due till Friday.